So today we're going to do section 2.3, limit laws. First, theorem 2.4, which is identical to the theorem that we mentioned last time in the last video. But being that they mention it again, I guess we'll also mention it again. That is, limit of x as x approach a equals to a. So this is section 2.3. Let's see. Okay, 2.3, which is limit laws. The theorem something 2.4, which states limit of s of x as x approaches a simply equals a. Well, that seems obvious, right? What else would it be? X, I just said x approach a. If x approach a, the limit is a. And even more obvious is the next one, which says if you have a constant, limit of constant that's just standing there as x approaches a, we already said is constant. It doesn't care what x does. It's staying as c, the constant. So as x approaches a, the limit is just c. So as now let's look at the examples. Actually, let's not look at the examples. Let's just move on. The next thing is theorem 2.5, which is somewhat more important, and which just says that generally speaking, the limit law applies to everything. For example, if you have f and g, okay, and then to evaluate the limit of, say, two functions f and g, then you can simply evaluate the limit of each function and add it up, such as this theorem, I mean. So limit of, let's say you want to figure out what the x as x approach a of f of x plus g of x. And that just equal to, you just calculate the limit of individual ones. That's equal to limit of f plus limit of g. Oops. Okay. Plus limit of g. And so on. This is with a bunch of conditions. Okay? I mean, obviously, if the limit of f has to exist. If it doesn't even exist, this whole thing is nonsense. Limit of g has to exist. They have to have the same domain or something. Anyway, it's just stuff like that. And they're not infinity, because you cannot add infinity, because infinity is not a number. But with all conditions being normal, then you can do addition or subtraction, okay, or multiplication or division. And again, division has the condition that the denominator cannot be 0. That sort of thing, okay? So, or even raise to some power, okay, raise to the power of 5 or billion, or take the root of something, as long as everything exists and makes sense. So that's theorem 2.5. And having said that, let's move along to some example. Let's see. Okay. Now the example we will look at is example 2.15. No, let's not look at example 2.15. Let's look at something else. Move along to some other example. All right. Okay. Flip. Is there a limit here? 3. No? Okay. Let's go to something interesting. Which is, what's this on? Page 163, which has this particular example. Okay. Now, from this point on, any example I do, please, after you watch the video, please redo it at home like it's a problem. That is, you write down the problem, you cover the explanation, see if you can reproduce it. And you might think, of course I can reproduce it. I can just watch you do it. Not necessarily. Okay, make sure that you know how to do it yourself. any example that I work on in the video. And that's how you get good at math. It's just one of the tricks. See, people don't know how do you be good at math. Well, you rework all the examples in the book. That's trick number one. So, I mean, I scored the highest in my math class. Just saying. Anyway, so going on. So let's look at this particular problem, which is not even an example. It's just something. It's on page. It's after example 2.16. Okay, so I'll write down 2.16, and you look after it to find this thing. But it doesn't matter if you find it. We're just going to do this. So let's look at limit of x approach 1 of x squared minus 1 over x minus 1. All right, now that looks like an easy enough problem at first sight. Okay, you just to calculate the limit, you just plug into each one, like I said. Addition, subtraction, division, doesn't matter, and then you calculate the results. So you get the limit. So like I said, you calculate the limit of each one, right? X squared minus 1 divided by the limit of x minus 1. And that gives you what? As x approach 1. So that's 1 minus 1 is 0. And this is 1 minus 1 is 0. Uh-oh. Now you got a huge problem. You may not divide by 0. And that's because I neglected to mention that the condition of division, as in all conditions, is that the denominator cannot be 0. Okay, if the denominator is 0, the rule doesn't apply. So we need to, and that's where limit problems gets interesting. So the way you, because normally if you just have to evaluate each one, you're just evaluating a function. It's no different, right? But here's where limit problems get interesting. And so what you do in this situation is you pull a trick. And in this case, the trick is called canceling. Factoring and canceling. So here's what you do. You factor this thing. So instead of this is wrong, okay? Wrong. And so instead of doing that, what you do is x approach 1, you factor this thing and then cancel something out. Mostly you cancel the 0 out. So x squared minus 1, that's the plus and minus from algebra, okay? It equals the plus and minus. That always equals to that. And then you just need to memorize that. Anyway, and then divided by original x minus 1. Now at this point, we will cancel this with this understanding. That is, your x is only approaching 1. It's not actually 1. Okay? We don't care what happens at 1. We only care about the area around 1. Something that's very close to but not equal to 1. Now in that case, if it's not equal to 1, then you can divide. You can divide by a number that's very small but not 1. Okay? I'm sorry. You can divide by a number that's very small but not 0. You may not divide by 0, but anything that's very close to 0 is perfectly okay. So we're doing the limit. So this is only something that's very, very, very close to 1, but not, so the denominator is close to 0, but not 0. In that case, you can cancel. So we'll cancel it, and this equals to the limit of just x plus 1 as x approaches 1. And what happens when x approaches 1? Well, x plus 1 is just 2. And that is the answer of this thing. You see, so you got around the dividing by 0 problem, and come out looking peachy. So all right, so that's the first example we'll look at, and let's look at the next thing. Next problem is calculate on limit. Right. Problem solving strategy. Moving on. All right, example 2.7, the same thing. You have something that's probably making the denominator to be 0, so a fraction or rational function expression is not whatever. The point is there's something rational, and your limit, you can bet that they're making it go to 0 so that you're stuck. So what do? You factor, then cancel. Yeah, so and that's the same. That's example 2.17. That's the same as this thing. So we'll move on, and a slightly different trick. Next, the next trick has to do with radicals. Example 2.18. So 2.18.18. All right, you have to do this thing, which has a radical in it. Limit of x approach minus 1. It may be slightly more interesting, or it might not be. Either way, we're going to do it. And remember, any problem I do, you need to redo it when you're done with this video to be good at math, if you want to be good at math. Okay? So, okay. Now, so there's that. As you can see, x is approaching -1 of all things. Because why? Because that makes the denominator 0, and you're stuck somehow. And then on top, it just -1 plus 2 is square root of 1 is subtracted, and it also equal to 0 if you put x as 1. So you got that 0 divided by 0 situation again. And so you are at a loss, right? But no worries. The way you get around it is you factor and then cancel out the 0 somehow, the 0 part of it somehow. So let's see, how do you factor this thing? In terms of radicals, there's a different trick, okay, that you pretty much have to memorize. So what you do is I think there's a name for this, the conjugate. Yeah. It's called a conjugate. Basically what it is you, you multiply this thing here by the plus version. Using this formula, what you're doing is using the old a plus b times a minus b equals to a squared minus b squared. Now, that's one thing that if you don't remember, write it down in your cheat sheet. It's very you use that all the time. So anyway, that's the principle, and and then we'll rewrite this thing so that we can factor the deal. What you do in this case is -1, okay, and you multiply by the plus version of what's on top. X plus 2 minus 1. I'll write down the original problem. And then you multiply by the plus version. And you think, how do I get to suddenly multiply by some random stuff? You don't. You multiply by the same thing on the bottom of your fraction. Okay, now when you multiply by the same thing, this value is just 1, which means you haven't changed anything yet. Yeah, you are multiplying by 1. And this is a trick. Okay, this is a big multiplication. And then and this trick by multiplying by 1 will help you do something. Okay, and so let's follow this formula. Remember, an object multiplied by the minus of, something like this will end up being the difference of squares. So we'll follow that formula and write this down. So this is a. Okay, a squared is just x plus 2. And then the 1 becomes a -1. And then on the bottom, you have the pile of stuff like this. What's that? You have, okay, this pile of stuff, which we will write it out. We're not going to multiply it out necessarily, because this might work itself out without having to do extra grunt work. Okay, as a mathematician, I try to avoid grunt work if possible. So so you got this. I forgot to write down the limit, so there's the limit symbol is still there. Yeah, it's there too. But anyway, we'll write down the limit symbol because and here's the limit symbol. I forgot to write it down, right? The limit hasn't changed. So next, this x is approaching -1. And at this point, what happens? At this point, what happens is that you are able to cancel. Okay, the big beautiful canceling that get rid of all the junk and make things look much neater. So you have x plus 1, okay, on top. I'll keep it in parentheses for no reason. And then the bottom, I'll repeat the bottom. X plus 2 plus 1. Okay, now at this point you notice that you have an identical thing which you cannot cancel when x is -1 because x minus 1 make the denominator 0, which is not acceptable. You can't do a thing if the denominator is 0. However, as we always remember, this is not x is not -1. It only approaches it. That is, we don't care what x is doing at -1. We're only talking about the immediate area around -1, all the numbers that's extremely close to it. Now, at that point, it's okay to cancel because it's not -1 yet. It's only close to it, right? So with that fantastic trick, you're allowed to cancel it, and then this thing becomes limit as x approach -1, 1 over this pile of stuff, which I will write it down here. All right. And so then at this point, then you can calculate this, okay, as x goes to -1. It becomes very close to -1 this is 1 and plus another 1. So you get 1 over 2. And that is the limit of this weird thing that end up being 0 divided by 0 or something, and then it's not obvious how it's done. And this kind of limit problem is more interesting because you're forced to use a trick to get around it because it's not obvious. Okay, things that are obvious are never interesting. You have to solve the problem, right? And okay, so that's example. Yeah, 2.18. Let's look at example 2.9, which is on page 166. All right. We will continue to do another example of how you pull off a trick in limits. This is example 2.19. And then here's your problem. Limit as x approach 1 of 1 over x plus 1 minus 1 half divided by x minus 1. As you can see, this problem is designed. Oh no, darn. Yeah, I forgot to put my headphone on. The problem with our headphone is I find that when I turn my head, my camera doesn't pick up my sound very well. But I guess it's okay. It wasn't a big loss. So moving on. So let's do this problem. As you can see that the denominator is 0 again. So whenever you have the denominator to be 0, let your mind think about this awesome formula. It's called difference of squares, right? Just like the one we had before, which equals to x8. The difference of squares, which is equal to a plus b times a minus b, right? And that formula is so handy, and we will use that here too. So you have denominator is 0, so now you're stuck. How do you get out of this mess? Um, Here's how you do it. You multiply everything by something, but see, x minus 1, you do the other one, okay? You do the x plus 1, and then you get this thing out and you cancel something, and then everything falls out. But first you have to do fractions, which is a bit of a grunt work, but every mathematician has to do some grunt work sometimes. So let's do the grunt work. You have well, okay. So let's do grunt work, a bit of grunt work, which is in this case fractions, how to solve rational expressions. The word rational means ratio. Ratio is fractions. So there's nothing rational particularly about it, right? So let's do this thing. X minus 1, and then that's least common denominator to do fractions, and you have to do this, which is 2x plus 1, and then that's 2 minus x plus 1, I think, in parentheses. Don't forget the parentheses or you're gonna get it wrong. The whole thing will collapse. And then you have to do it all over again. If that happens, whenever you do a math problem and it doesn't come out like the way the answer shows, do it again. So, and then you have to do this. Ugh. And so that equals to and then you have to in the meantime, okay, we still have to now we still have to multiply by the other thing, okay, which is multiplied by the other one. Okay, we have x minus 1, so we multiply by x plus 1 to achieve the difference of square effect. So x plus 1. Okay, now this is just 1, so you haven't changed anything. All right, so that equals to 2 minus 1, that's 1 minus x over here for that part. And then divided by, oops, that is, this cancel out with that, divided by 2. And then all over x squared minus 1. And then that equals to, I think, yeah, that looks good. And then you that equals to 1 minus x over 2 times x squared minus 1. If this isn't clear for you, please review the how to solve rational equations, expressions, simplify something, okay? And anyway, so let's move on. And then so you got this, and notice there's some canceling happening. And what does that do? Let's move on, okay? Actually, there's even more canceling happening, which is awesome. Okay, now so let's keep going. There's a limit here. Let's not forget the limit. Okay, now we have gotten to here, limit. Okay, now we have gotten to here. Actually, there's no need to multiply it out. We'll keep it that way. So we'll keep it that way. 1 minus x is the same as negative of x minus 1. And then this is 2 times x plus 1 times x minus 1. Okay, that's the original. now you can cancel that out. So now you have the limit of minus 1 over this part get canceled out. So you have 2 times x plus 1. That's right? Yep. And at this, and x is approaching 1. And that makes it a very neat solution. See what happens when x approaches 1? Well, that whole thing, that's 2. It approaches 2 times 2 is 4, and there's a negative, so negative 1 over 4. That would be your answer to this limit. And as you can see, there's a bit of grunt work involved, especially with rational expressions, and you just have to suck it up and do it. Okay? And make sure you know how to do it too. And be sure to repeat this example at home. When you are done with this video, just what you do is write down the problem, then cover the solution and see if you can come up with this yourself and get to the right answer. If you don't, then figure out what you got wrong, especially by reviewing rational fractions. If you get it wrong, if you can't get it, there's only one reason. You forgot how to do rational fractions. You got messed up in here somewhere. It's very easy to get messed up in this kind of thing, but is straightforward. Okay, just look it up how it's done. So anyway, moving along. And then next, we have